Hello and welcome back to Around the World in 80 Telescopes, a live 24-hour webcast that is part of the 100 Hours of Astronomy project for the International Year of Astronomy. You're joining us at the European Southern Observatory headquarters near Munich in Germany as we visit some of the most advanced telescopes both on and off the planet. We're now going to CHARA on Mount Wilson in California. Before we join them live, let's find out about them in this video.
It's very difficult to wonder about life, our lives, life on this planet, life on other planets, without first wondering about stars. Stars are the substance, the engines that build everything in our known universe. And without understanding stars, we'll never understand where planets come from and where we came from.
We have one star which we've been able to study in exquisite detail, and that's the Sun. And that's because it's so close by. You can actually take pictures of it and be able to see sunspots and see solar explosions. And the Sun's the only star that we've been able to look at in this sort of detail. And this is where you need special techniques to look at other stars and see them in this sort of detail that has been previously only done for the Sun.
CHARA stands for Center for High Angular Resolution Astronomy, which basically is the theme of what we do. Resolution is the ability to see fine detail in distant objects, and unfortunately distances are so great in astronomy that resolution has always been something that has been unattainable for most of the objects we look at. Stars, for example, are so far away that even with the biggest telescopes that we've ever built, most of them appear just as points of light. But the kind of problems that we have to solve involving measuring sizes of stars require us to build telescopes that are not just tens of meters across, but hundreds of meters across. And those are completely unfeasible for the indefinite future. So we get around this problem by synthesizing a single giant telescope with arrays of smaller telescopes. The CHARA Array is a collection of 6 telescopes that are arranged on the ground in an area that more or less kind of covers the area that a single large telescope mirror would have. And what we then have to do is to have relay optics, many mirrors along the way, to effectively move the beams as if the telescopes were all placed lying on this optical mirror that we're trying to synthesize. And that's been the real problem with interferometry, being able to precisely control the beams of light to attain that synthesis of a single mirror.
This is part of the daily alignment check. Essentially, we send a laser beam backwards through the system and check that it hits all the points that it needs to hit. One of the targets is right here. Spot on. It's very important that from the star all the way to the point inside the instrument where we bring the light beams together, that the light travel time is exactly the same. Now, because the telescopes are at different elevations and different parts of the mountain, and the Earth is constantly rotating, these paths are forever changing. So we have to continuously adjust these paths within the instrument using a thing called a delay line. In interferometry, timing is everything. And that means that we have to get the light from all 6 telescopes around the mountain into this room at the same time. While we can't control the speed of light or the time it travels, what we can do is change the path length over which it travels. And that's what this long tunnel is for. These carts are optical trombones, such that we can add and subtract path length and make the light from each of the 6 telescopes arrive at the same time at the back end, so that we collect the data to make our pictures.
The ability to make images with interferometry is dependent upon how many telescopes you can put into the mix. As you add more and more telescopes, you get to fill in more and more pieces of this image that you're trying to synthesize as if you had a big telescope. So in the end, you're never going to get all the way there because you're never going to be able to put a telescope on every piece of the landscape that is pretending to be your overall telescope. But if you do enough of it, you can actually get data that you can't get anywhere else.
The bread and butter work, if you will, of the array is measuring these fundamental parameters for stars, their sizes, their shapes, masses, distances, luminosities, and things like that. And so we produce images that are based on theoretical models that incorporate the observations, the measurements that we make. For example, we have been looking at stars that are rapidly rotating, spinning on their axes in a matter of hours rather than, in the case of the sun, about a month. And these stars are spinning so rapidly that the centripetal acceleration makes them bloat out at their equator and flatten in at the poles. All of these stars that we look at would just be points of light without interferometry.
We're able to see detail that no one's ever been able to see before. Throughout history, people have been building new telescopes and discovering things that they weren't expecting to find. The kind of measurements that we can do will, for the first time, really test the models that we have of stars, how stars work, how they're born, how they live and how they die, how planetary systems might or might not form, and ultimately about whether life will form upon these systems. And since our understanding at the moment is that we came from the stars, well, that's where we have to go to find out about things.
We're now going live to CHARA. Hi there.
Hello.
Okay, so you can hear us. That's good. Can you tell us, actually, what does CHARA stand for?
CHARA is the Center for High Angular Resolution Astronomy.
Great.
So we're a group of astronomers who are interested in very high resolution information about stars.
Okay, great. And can you tell me a little bit about yourself and what you do for the observatory?
Yes, I'm the Associate Director of CHARA, which means I'm the guy on the spot here on the mountain running the system and making sure that it continues to run and our night assistants don't run away.
Is that a problem?
That's not a problem, is it? No. No, that's not really a problem.
Okay, could you tell us a bit more about the observatory? You said you're interested in looking at stars with very high spatial resolution. Can you tell us a bit more?
Well, we're interested in fundamental parameters of stars. How big are they? How hot are they? How much mass is in them? What sort of orbits are they in? What do their companions look like? Is there a dust shell around them? Is there planets there? We're mostly interested in this stuff to understand the life cycle of stars. We want to know what makes stars tick. Ultimately, to find out about solar systems and how they might form, but just also about stars themselves. Stars are the engines of most matter that we know of, so they're of great interest to us. And in order to learn about stars, we need to measure very fundamental things about them, which it turns out is extraordinarily difficult to do. Stars, while they're very large objects, tend to be very far away, and that makes them very small to our view. So small that you need an instrument like ours to see them as anything except a dot.
Mm-hmm. Okay, so what kind of stars are you yourself interested in? Do you focus on a specific kind of star, or is it more the technique that you're interested in?
The research that I do in my copious free time is centered around binary stars, that is multiple star systems, stars that are trapped in each other's gravitational field and are rotating around each other. That's in fact what we're observing right now. The conditions are not great, but data is still coming in. Binary stars, because they're orbiting around each other, if you can measure this orbit precisely, you can use Newton's laws to calculate the masses of these stars. And the mass of a star is probably the most fundamental parameter about a star. If you know the mass of a star,